Hello and welcome to the third lesson on alkenes. So this lesson covers the addition reactions of alkenes. This does not cover the electrophilic addition mechanism that comes in the next lesson. And so instead it really just looks at the principles behind addition reactions and how to write symbol equations for addition reactions and think about the formulae of products. So I'm going to start with some starter questions as usual. You need to pause the video and attempt to answer these before we look at the solutions. If you're just waiting for the solutions to come, you're wasting your time. Make sure that you do have a go at them. If you can't do everything, it's not the end of the world, but you need to have a go. So pause the video and answer the questions. Okay, so what we should have is Z pent 2-ene for the first question. So what you're comparing here is carbon versus hydrogen on both sides, and in both cases the carbon is going to win. So there's no complications here really. It should be, really straightforward. That makes it the Z form of this isomer. And the double bond is located on carbon 2, which makes it 2. There are 5 carbon atoms in total, so that makes it pent 2-ene. Z pent 2-ene. The molecular formula for any form of pent 2-ene, whether it's E or Z, is C5H10 because it's a simple alkene with one double bond, so it follows the CnH2n general formula. Then for the combustion equation, it has to very specifically be carbon monoxide that's your carbon-containing product because the question asked for a toxic gas, so it can't just be carbon particulates, and it should look like that. Okay, so here are the facts. Alkenes are reactive. They will undergo addition reactions. This is because of the nature of the carbon-carbon double bond, which is a region of high electron density, and it is attractive, therefore, to electrophiles. Okay? Now, we're not going to explain fully how electrophilic addition works in this lesson, like I said, but we might as well establish this and sort of set terms to begin with. If you need to pause the video and make your notes, now's the time to do it. Okay, so addition reactions are essentially, reactions where you add stuff to a compound rather than, for example, a substitution reaction where you swap one thing for another, or an elimination reaction when you just kick some atoms out of a compound. So addition is where you add something, and in this case it's adding stuff at the carbon-carbon double bond. So let's have a look at what kinds of things alkenes undergo addition with. So there are 3 sort of classes of compounds that we generally look at in A-level chemistry. You could be asked to look at other ones, but this is these are the most common examples. So classified in 3 different ways. One is hydrogen halides, the next is halogens, and the final one is concentrated acids. I've given an example in each of those categories, but it's important to point out that hydrogen halides could also refer to HCl or HI or HF or whatever. It could be any of those, okay? HBr is the one I've chosen as my principal example in this lesson and in the next lesson because it is the one that is referenced in the AQA A-level chemistry specification. So hydrogen halides refers to things like hydrogen bromide, hydrogen chloride, hydrogen iodide, and so on. Same kind of logic applies to the second category. The halogens refers to the group 7 elements in their diatomic molecular form. So for example, bromine or chlorine or iodine or fluorine, okay? Now, I've used bromine for the same reason that I used HBr. It's the one that's referenced in the A-level chemistry specification. Chances of you being asked about the other ones are a bit slimmer, especially for things like fluorine, because fluorine is very reactive in other ways as well. So bromine is the example I will use initially. Then finally, for concentrated acids, by far and away the most common one to encounter here is concentrated sulfuric acid, but just for the sake of completion, you might, in a challenging question, also be asked to look at conc phosphoric, okay? We're not going to worry too much about the acid reaction yet. We won't really look at the products of that properly until we do the mechanism in the next lesson. We're going to focus mainly on the first 2 categories. So as usual, if you need to pause the video and make your notes, now's the time to do it, or whenever whenever you feel appropriate. So then let's have a look at how an addition reaction kind of works, right? we talked about how we add stuff across the double bond. That's a phrase we sometimes use. The idea is that in an alkene, there are two bonding pairs between the two carbon atoms, as opposed to just one. So I've just highlighted one of those bonding pairs. Now, in reality, the bonding in an alkene is a little more complex, and there's electron density kind of above and below both carbons. But at A level, we don't really look at that very much, at least not until we look at a compound called benzene later on. For now, just sort of recognize that there's more electrons between those two carbons. There's a higher electron density between those two carbons than there would be in an alkane. That's what makes them reactive. Okay, and when we talk about adding stuff across the double bond, we're talking about the fact that actually the double bond, one of those bonding pairs is going to be kind of broken apart. It's going to be used to form new bonds with other atoms. And that's what an addition reaction is in the context of alkenes. So in this case, what we've got is the addition of a hydrogen atom and a bromine atom to two separate carbons on other ends of the double bonds. And so the equation, if you want to call it that, using kind of the displayed formulae, looks like this. So it's just important to point out, in an addition reaction with an alkene, you're going to get new bonds forming on adjacent carbon atoms where there was a double bond before. Okay? So that bonding pair that was highlighted in blue on the left, right? It's no longer a bonding pair between the two carbon atoms. Instead, we now have new bonds forming to a hydrogen atom and a bromine atom separately. Now, in reality, the actual kind of steps behind this is what we look at in the mechanism. But for now, that will do. It's also probably worth pointing out, to be fair, that in hydrogen bromide originally, there was a bond between the hydrogen atom and the bromine, which is no longer present. The hydrogen and the bromine are no longer attached to each other. They are now attached both to to separate carbon atoms in the organic product. So, a very similar example would be if you had a halogen, okay? If you add bromine across a double bond, it's the same kind of idea. Once again, in the bromine molecule, you actually have a bond between the two bromine atoms. That bond is broken, and the bromines then separately form new bonds to adjacent carbon atoms. It's exactly the same principle. There are complications to do with addition reactions, to do with the nature of the electrophilic addition mechanism, but we won't really encounter them at all until a couple of lessons' time. But let's say if we look at a bigger alkene, sometimes that causes problems. In this case, it's okay, right? The logic's still exactly the same. We just have to recognize this is the site of the reaction. That's where these atoms are going to get added. And so when we're kind of drawing the organic products, we need to bear that in mind, right? They have to be in the middle of this molecule. In reality, for this thing that we form called 2-chlorobutane, actually, the chlorine could be in either position. It wouldn't make any difference to the name, right? But I've chosen to put it on the right, okay? So what I'm saying is the chlorine could be there and the hydrogen could be there. It would make no difference in this case. Further down the line, like I said, there are complications with that, but that's not to worry about for now. So over to you, basically. You've got a task, right? You need to think about the two things that are reacting together, all right? The alkene and the thing that's reacting with the alkene. You need to come up with a structure, a displayed formula for the product, and have a go at naming it. So what you need to do is pause the video and try and draw the product of these reactions. The one that's in red is a little bit more tricky, and so if you can't do it, don't feel bad. Okay, let's have a look at some solutions. For the first example, we should get chloroethane. No number needed here, because wherever you put the chlorine atom, right, that's carbon 1, basically. And whenever that's the case, you don't include the number. because it's redundant. It doesn't, it's superfluous. It doesn't need to be there. So that thing's just called chloroethane. Okay. In this case, we had propene as our starting alkene and we added a halogen to it. Okay. This time we do need some numbers because there are 2 iodine atoms. One of them is attached to carbon 1. The other one is attached to carbon 2. So we call it 1,2-diiodopropane. If you weren't totally clear about the name, but you did get the structure right, don't worry too much. Okay. It might just be worth reviewing some of your nomenclature and isomerism stuff from the start of year 12. Here we have 3-bromohexane. Notice, as usual, I've put it on the right-hand side of where the double bond was, right? But it's still 3-bromohexane. Even though from left to right, you're counting 4 carbons along, from right to left, you're counting 3 carbons along. And in this case, because bromine's the only sort of substituent, the only thing that's attached to the hydrocarbon chain, you're going to count from the end that gives you the lowest number, because that's the kind of rule about how we name organic molecules. So 3-bromohexane. Finally, the one that was kind of there as a challenge question. It's not horrible, but anytime you include kind of a cyclic compound, it does complicate things a little bit. We'd call this 1,2-dibromocyclohexane. So we had cyclohexene, where there was a double bond, and we've added 2 bromine atoms. And as usual, we have to sort of say what their position is relative to each other. 1,2-dibromo. You can't just call it dibromocyclohexane because that implies that you don't know where the bromines are. Okay. Right then. Here's something that's kind of relevant to what we're looking at now. Okay. So the bromine water test is a test tube reaction that we use basically to test for the functional groups of alkenes. All alkenes will react with bromine water. So if you mix a suspected alkene, something that you think is an alkene, with a solution of bromine water, then you will get this color change and it will confirm if it is. If it's not an alkene, then you will get no visible change. The bromine water won't undergo a color change. So bromine, when you dissolve it in water, has a kind of orange color. Sometimes it's described as yellow, right? I would go with orange. It's really concentration dependent, but orange is a completely safe bet, okay? So that orange color, the orange color of the solution, turns colorless if an alkene is present. So if you mix, for example, bromine water with ethene, if you bubble ethene gas through bromine water, then the orange color will go away, it will become decolorized, and you will get a colorless solution. The reason that this happens is because the bromine, which gives the solution the orange color, the bond between the 2 bromine atoms, as we talked about earlier, is being broken, and the bromine atoms are forming new bonds to form 1,2-dibromoethane. This works with any alkene, not just ethene, okay? And it's an important, test for a functional group that you have to know for A-level chemistry. And in fact, it's part of GCSE as well, so you might well be familiar with it already. I'm just making the link really between this test tube reaction and the fact that we're looking at addition reactions across a double bond. The equation would look something like that. So ethene gas, bromine in solution, and then I've used the state symbol L to describe 1,2-dibromoethane. The only reason I've done that really is because it's not soluble in water. So what would actually happen in this reaction is you'd get kind of a separate layer probably where the halogenoalkane that's been formed would kind of float if it's less dense than water. I haven't checked the density of it, but there would be separate layers, put it that way. Right then, to finish up the lesson, you should really put your notes to one side and try and test yourself. The reason for that is it's very easy to assume you know everything if you're able to constantly reference your notes. I'm not saying there's anything wrong with that when you're doing revision and what have you, but you also need to sort of check check your own knowledge and understanding sometimes as well. So you should put your notes away, cover them up, and get a scrap of paper or a whiteboard to answer the following questions. Here they are. So it's a nice mixture. Okay. Pause the video and have a go at answering those. Then quick look at the solutions before we finish up. Have you answered them? I hope you have. Here we go. So for the first two, we've got strict definition, a compound that contains hydrogen and carbon only. That's a really important part of the definition. The general formula for alkenes is CnH2n. Then for the chain isomer of hex-2ene, what I've done is I've actually started with hex-2ene. So this first one is not a chain isomer. It's the molecule that we're kind of starting with in our puzzle. So my first logic was, well, what happens if I take one of these carbons and put it somewhere else, right? So that's what I did, and I made this molecule, okay? So that would be 2-methyl pent-2ene. Doesn't have to be that you came up with that one, but that's the first one I came up with. Then I considered what would happen if we had the methyl group on the other side of the double bond. So that's 3-methyl pent-2ene, and that actually has geometric isomerism as well. The question wasn't really about that, but it does. So I've made a small reference to it. You could have the E form or the Z form. It doesn't really matter. Or in my case, I haven't shown the geometric isomerism at all, and that's fine too. Then what about this scenario? What if we shorten the main chain and we now have 2 methyl groups? So this would be 2,3-dimethyl but-2ene. Okay. Definition for empirical formula was the answer to question 4. And bromine is simple molecular. Very easy to kind of forget about that sort of stuff, but bromine exists as a simple molecular structure. Okay, next time we'll look at the electrophilic addition mechanism.